Hello, everyone, and thanks for attending this talk about our Interspeech paper called Heterogeneous Target Speech Separation. My name is Efthymios Dinis. I'm going to present the paper. This is joint work with Gordon Wichern, Azun Subramanian, Paras Maragdis, and Jonathan Leroux. So audio source separation as a task is the co-occurrence of multiple sound sources where one needs to extract the independent sound sources from the mixture. When all of the sources are needed, this is usually called unconditional source separation, whereas when there is some kind of condition or target that we can specify the sources, this is called target source separation. So target source separation first solves the disentanglement of the sources problem, but also solves the alignment of the estimated sources to a proper order, as we can see here, using a conditional separation network, using some kind of condition and then only targeting one of the source. So this paper is going to talk about what kind of conditional targets that we can use sometimes could help significantly the performance of these models and how we train those models with such conditions. So slicing an acoustic scene has multiple solution based on what the user wants. So there are multiple ways to describe exactly the same source, as you can imagine, saying, for example, giving a semantic concept or something related to the energy of the source, something like that. So, for example, here on the right, we can see a specific instance of the heterogeneous target source separation, where you want to isolate a speaker based on different semantic concepts such as the gender of the speaker or the distance from the microphone or the language that the speaker talks or the energy of the speaker would be the loudest or the less than energetic speaker. So permutation invariant training, as we said before, the way that we train those kind of models is that we backpropagate the minimum loss under all the permutations of the estimated speakers. And this is a way easier than target source separation because, as we said, we don't need to solve the problem of the alignment of the sources. Heterogeneous target source separation now, in order to train models with our own method, with this method, we need first to generate a mixture of set of sources, as we have here, and then we can sample a discriminative concept to create a target waveform, as we show here on the right, which is the red one. But that target waveform could contain more than one sources, and as you see here, the discriminative concepts could refer to the same kind of condition characteristic function, which is, let's say, the shape, or different things that belong to only one of the sources. And then we train the model under a targeted L1 loss, as we see here, by fitting in the sample discriminative concept to the conditional separation network, and then backpropagating the targeted error. But we see here that as discriminative concept, we could use anything that is in our metadata. So, for example, if the conditioning characteristic function would be the distance from the microphone, one could use far or near. Or if the language spoken is the condition characteristic function, the discriminative concept could be give me the French, the speaker who speaks French. In order to train and evaluate our models, we generated 3 data sets that we're going to make available online, which have different metadata, as we see here. The first one is the Wall Street Journal, which is an anechoic data set, which has the energy and the gender information for the speakers. Spatial Libre Speech is a reverberant version, which is still an English speaker data set, which on top of that, it also has a spatial location of the speakers, whereas spatial Voxforce is the hardest data set out of the 3, which also has 4 different languages, 3 more than English, and it has the energy, the language, and the spatial location of the speakers. As a model, we use a conditional variation of a state-of-the-art system called pseudo-MRF, which has us in one hot conditioning encoding vector based on all of the semantic concepts. And once again, here for the energy could be the loudest or the most silent speaker. For spatial location would be the far or near field. The language would be the 4 different languages that we have here, and the two genders. So what we do here is that for our model, we have a film modulation layer right before the input of each one of the Yukon blocks, the stacked Yukon blocks that we have, and we always estimate the target source and the other source, which is like the non-targeted source with a mixture consistency layer on top. Also, another thing that we need to underline is that this kind of conditioning mechanism adds a really low overhead conditioning mechanism for including all these conditions and all these discriminative concepts, as we said before. In order to train, we sample a discriminative concept, we said, given some kind of sampling prior. And then what we do is that we generate the target estimate, the target source, and the other source, and we use the L1 norm based on these two with equal weight, and then we train our models using those kind of different conditions. So as we see here, WSJ has a slightly different input SNR distribution, and from spatial Voxfords and spatial Librespace, based on which one of the two datasets is matched with, follows exactly the same distribution. And now, in order to evaluate, we always use scale invariant signal to distortion ratio on the target source, which is actually the task. So for the first results, we can see that the single condition models, which is the top line, the first row here on this table, is a set of different models trained and evaluated on each one of the conditions here. And comparing that to the permutation variant training oracle, which, as we said, doesn't solve the alignment of the estimated sources, we see that it's almost always better than that. So almost this also holds, except of the language condition for the heterogeneous training for in-domain data. So when we train and test on the same conditions as we see here, which has a huge improvement for both in-domain heterogeneous training and cross-domain heterogeneous training. And also what we can see here is that those numbers are also better for the cross-domain heterogeneous training compared to the permutation variant oracle by a very large margin, sometimes for up to 2 or 3 or more than 3 dB, as we see here in the spatial Librespace. And an even more important setup than that is what happens with those conditions that we don't have metadata for that specific data set. And as we see here, our cross-domain heterogeneous training can help those models surpass permutation variant training that actually has access to all this kind of data, which is a very important aspect. Moreover, what we can do is that we can explore this kind of trade-off for between the percentage of degenerate and easy cases. So here, for example, we have this kind of degenerate case where our target source waveform is always the mixture if you have a same gender mixture and same gender conditioning. So what we do is that we test for the cross-gender conditioning, which is here on the orange, and the energy conditioning as well. And we see that it drops as we increase the sampling prior of sampling a degenerate case. Whereas on the bottom here, we see that the opposite, that effectively we become better and better at actually getting good performance at reconstructing the mixture in this degenerate case. But as you can imagine, this is not ideal, because we don't want to overfit in our model in those cases. So what happens is that there is actually an optimal point for both gender and energy conditions up here, where we can also train and learn something robust for the degenerate case, while not dropping significantly in performance for the usual cases. And this also happens for only by including 0.4% of degenerate cases. So the next thing, which is super important here, is that what we call a bridge conditioning. So what happens here is that you miss some kind of data for, let's say, spatial Interspeech for the gender information. But what happens is that you can have a mismatched case, mismatched data set like Wall Street Journal, which is anechoic, so it's not reverberant, but you do have access to gender information. And what happens is that we see here that our model gets to learn to condition on this kind of gender information. We see here that if we remove this kind of bridge conditioning on the energy, which is the easier semantic concept that drives this network towards understanding the generalization, we have some kind of performance drop. There is also a performance drop when we include ambiguous cases, as we see here. So that means that the network gets to see around 0 dB energy conditionings. So that means that the energy condition is not so easy anymore. So that means that making this bridge condition really easy helps the network disentangle the sources and also learn the cross-domain generalization. And also what happens that we also have a huge performance drop when we drop the in-domain data, as we see here. And comparing the numbers of our proposed approach, we see that we are always better than permutation variant training trained on all this data. And actually, a very important aspect is that this number for the cross-domain data, metadata that we don't have for the gender in spatial Interspeech, we're actually going pretty close to a model which is an oracle, because it doesn't solve the alignment problem and also has access to those kind of data. As a final thing, in order to understand the usefulness of this kind of bridge conditioning mechanism, is that we see here that we can learn a harder condition using an easier one. So that what we show here is that for the leftmost point, we have two conditions. First of all, the language conditioning, which the evaluation trace is shown here on the orange one, and the blue one, which is the spatial location conditioning. And the leftmost point means that we only train 100% with spatial location as a condition, whereas the rightmost point is that we only learn using language condition. So the easier spatial location drops almost monotonically when decreasing the amount of training data in terms of spatial location, but this doesn't hold for language conditioning, interestingly, because the best model that we can hope for getting for both conditions is around a specific target. So it's really important to find this kind of sampling prior and make our models robust in order to train those things. So in order to conclude, heterogeneous target source preparation is a new paradigm in terms of source preparation, and specifically conditional source preparation, where one can slice the acoustic scene based on different non-mutually exclusive signal characteristic conditions and conditional concepts. And one can also consider using different definitions of those conditions based on and or. So our results show that heterogeneous condition training improves upon Oracle permutation variant training, which doesn't solve the alignment problem of the estimated sources, and also improves cross-domain generalization at different concepts and different datasets, and also can remain robust under degenerate cases when finding this appropriate sampling prior. In the future, we would like to apply our method towards a variable number of sources and pairing our method with less supervised approaches, and extend our heterogeneous training to other kind of queries, which might include natural language queries. I would like to thank you so much for attending this talk. I would be more than happy to answer any of your questions, and see everyone in the Q&A session. Thanks so much.